Proponents of the Apollo hoax theory will often put forth as evidence the lack of stars in the lunar sky in photographs from the various Apollo missions. This bit of so-called evidence has been debunked time and time again, and the explanation that the exposures used on the surface of the moon were far too short to capture the dim light of the stars rings true to even the most amateur of photographers. But the ironic and somewhat dishonest part of this claim is that there are nearly 200 photographs of the stars taken from the surface of the moon from the Apollo 16 mission. That this is wholly ignored by those who claim that man never set foot on the moon belies the fact that these photographs are some of the best evidence proving that the Apollo missions were very real. Why is this? Because in 1972, there simply was no way to fake these photographs. If these were just any old pictures of the stars, it would be pretty easy to fake. A picture of the stars taken on Earth would be fairly indistinguishable from one taken on the moon. But what makes these photographs from Apollo 16 special is that they were photographed in the ultraviolet spectrum, a part of the light spectrum that is invisible to the naked eye. The experiment was dreamed up in the mid-60s by Dr. George Carruthers of the Naval Research Laboratory in Washington, D.C. Carruthers is a physicist and inventor who has enjoyed a nearly half-century-long career specializing in the study of ultraviolet light and astrophysics. Aside from the work on the Apollo 16 mission, he designed the rocket experiment, which was the first to detect molecular hydrogen in space. In the mid-80s, he designed a rocket experiment that captured the ultraviolet image of Halley's Comet. And in the 90s, he was part of the independent study review that helped design the Hubble Space Telescope. Most recently, he has led the way in the UV photography of the polar aurora. So why is the study of ultraviolet light so important? Dr. Carruthers explains. The far ultraviolet is of great importance to the astronomer because it allows the detection and measurements of common elements, hydrogen, oxygen, nitrogen, carbon, and many others, in their cool, unexcited state. This allows more accurate measurements of the compositions of interstellar gas, planetary atmospheres, etc. The ultraviolet also conveys important information on solid particles in interstellar space and provides for much more accurate measurements of the energy output of very hot stars. But why send the observatory all the way to the moon? Seems like a long way to go for a few hundred pictures. Simply put, the observations couldn't be made on Earth, or even in low Earth orbit. As a picture from the Lunar Observatory shows, there is a surprisingly dense coat of hydrogen surrounding the Earth, the veil of which shines brightly in the ultraviolet light from our own sun. This hydrogen wholly obscures observation from Earth. Additionally, the vantage point from the moon allows a convenient place to observe the Earth itself. The strange equatorial airglow bands can be seen in many of the photos of Earth, the subtleties of which are illuminated in these false color renditions. When Carruthers published the pictures from the Lunar Observatory 2 months after the return of Apollo 16, astronomers were glimpsing a part of their own universe that no one had ever observed before. The bulk of Carruthers' ultraviolet photographs were new information. There simply wasn't any information available at the time to be able to fake these photographs. Dr. Carruthers' invention of the first lunar observatory marks the crowning achievement in his career and a notable turning point in astrophysics and astronomy. For the first time, astronomers had the chance to observe the universe in a different light. The information attained from the Apollo 16 lunar observatory is a cornerstone in the science of deep space observations beyond the visible spectrum. But how do we know these shots were really taken on the moon? Maybe they were taken by a satellite. This is doubtful on its surface, if only because we know the photos were shot on film. It was prohibitive to design a satellite to take film photographs, as there was no way to ensure the film could get back to Earth. But we can take it one step further and show there was only one way the photographs could have been achieved. Because the experiment included not only photographs of the stars, but also pictures of the Earth with the stars in the background, we can confirm not only the place, but also the time the pictures were taken. This exercise was first proposed by William Keel from the Department of Physics and Astronomy at the University of Alabama in the July 2007 issue of Skeptical Inquirer. For the purpose of thoroughness, I'll be using a different photograph than Keel did in his exercise. There are plenty of photographs to choose from. I like this one because of the striking view of the geocorona, and because it is so close to the beginning of the roll of film when astronaut and mission commander John Young began the Lunar Observatory experiment. 4 stars shine brightly in a row and will serve as the marker to figure out where our vantage point is at. Using a stargazing program like Celestia, which is available to download for free, we can attempt to recreate the shot. According to mission transcripts, photography of the Earth started at 120 hours and 33 minutes into the mission, which puts the time at around 1800 on April 21st, 1972. Plugging that into Celestia, we find that from the perspective of the Apollo 16 landing site on the Moon, Earth is riding along the back of the constellation Capricornus. At first glance, it might seem the stars don't match up. Some of the brightest stars, such as Deneb Algety and Nashira, the stars that make up the tail of Capricorn, don't even show up in the UV photographs. For the most part, our 4 bright stars in the UV spectrum are much dimmer in the visible spectrum, but they are easily identified as Tau Capricorni, Iota Capricorni, 30 Capricorni, and Epsilon Capricorni. No other stars in the sky will create this specific configuration. Why some stars shine brightly in the UV and others not at all is dependent on the physical characteristics of the stars itself, a fact that Carruthers' lunar experiments helped illuminate. Seeing that the stars and the Earth match exactly the original photographs, we can look down at our feet and see that we are, in fact, located directly on the surface of the Moon. This exercise gives us a degree of precision that allows us to place the time the photograph was taken down to the exact hour. Even by a matter of few hours, we can see a drastic difference in the location of the Earth. So it turns out the photograph was taken at the exact moment John Young claimed to have taken it. Carruthers' ultraviolet spectroscopy has provided new and valuable information into the study of the universe, information which has been confirmed by additional studies into the UV spectrum, such as the TD-1 satellite, which completed its point-by-point survey of the sky 2 years after the return of Apollo 16. The nearly 200 photographs taken of the stars and the Earth from the Moon in April of 1972 stand as some of the best evidence proving they went, if only for the fact that they would have been impossible to fake.